Hey everybody, today we are going to do RC circuits. I'm Michelle Maharbis.
And I'm Vivek Subramanian. Let's get started. This class of circuits we're going to look at are extremely important. These are so-called first-order circuits. You'll see why as we work through the math of these. But they turn out to be pretty important circuits when we start thinking about how circuits work in the presence of time-varying signals. This then brings us to some important terminology with respect to the response of these circuits. First, when we talk about any of these circuits, we talk about specific responses to externally applied voltages or externally applied currents. And we specifically define two major types of responses. The first type of response is called a natural response. That would be you take a circuit, you've got it in some condition, and then you remove your sources. And you see how it responds without any sources present. And that's called the natural response. A classic example of that is you'll have a circuit that has power applied to it, and then you'll pull the power off, and you'll see what happens to that circuit once the power is removed. The complementary type of response is called forced response, and that would be a response to an external source. Now you can put those together to get the complete response of the system, which is natural and forced. Now why do I introduce these terms? Because this is actually how we're going to break up the problems. We will look at how circuits respond in terms of their natural response and how they respond in terms of their forced response, and then we'll be able to get a complete picture of the responsiveness of a circuit. As we've already pointed out, we are focused on time-varying circuits right now, and in particular, I gave you this example where I'm pulling off the source and I'm seeing what happens. So I'm looking how things change with time due to a temporary change in the behavior of a circuit. We call that transient response. In other words, the response of a circuit to a change in something as a function of time. Steady-state response, on the other hand, is a system that describes a circuit that is time independent or is periodically repetitive, and we'll cover that later, but you've already seen an example of that in the capacitor and inductor section where we looked at how it responded to sinusoids.
So I guess what you're saying is that these two boxes, source dependence or time dependence, are somewhat different but complementary ways of looking at what the total response of something is going to do over all of time.
That's correct.
There's just sort of different ways of parsing the contributions to the final signal that you're going to get as an answer.
That's correct. And in this section, we're really going to focus on transient response. And within transient response, we're going to look at natural and forced responses. And then in a future section, we'll talk about the steady state response in more detail.
Fair enough. So let's do something real basic first, and that's just to clarify what we mean by transient. Very quickly. The transient response really represents the first thing, the initial reaction that happens after some change, okay, in the circuit. And we're going to be using this little gimmick a lot. And the gimmick is there's a switch. So here's a circuit. We're going to put all sorts of things in here for you to analyze and give you a hard time. And at t equals 0, this switch was closed. In other words, that this source and this resistor were connected to the circuit, and it was open. And then, as the arrow indicates, at t equals 0, we close it, so we short it out. But you can do variants of this. So I can have this circuit open, this switch open at t equals 0. I can have it closed at t equals. But what this switch does is it gives us some abrupt change. So notice here, for example, this is an example. You could see that as it was 0. This current was 0. As soon as I connected it, it jumped to some value, and then it decayed away. And so you had an initial value and some final value, which we'll call I infinity. It's an example of something that could happen.
Let me take a guess at a system that could give that. So what if I had a capacitor in there? You told me earlier that when I have a capacitor, when I first connect it to a voltage, it starts charging very rapidly, and then as it charges up, the current drops off.
Yeah.
So could that be something like that?
That's a suspiciously well-informed guess, Vivek. Yeah, obviously, yeah, absolutely. So because capacitors, and in a little while in another module, inductors store, you'll see that we can use combinations of resistors with these other things, these capacitors or inductors, to play games with how energy comes into or out of these capacitors. That's exactly right. So in this top example, we've got this transient looks like a decaying exponential. And here is a more complicated example. The initial transient looks like something decaying, and then it steadies out to its steady state response, which is just a sinusoid. So transient is that initial thing that happens, and it's going to go away. That's why it's called transient. The circuit will eventually stabilize at some final value different from what the initial transient is. Transients are very common in digital circuits, in analog circuits, and analyzing was a very big deal because they cause all sorts of problems, in fact.
Okay, now let's consider a circuit, and let's first start by figuring out the behavior of an RC circuit in DC. And what do I mean by an RC circuit? It's a circuit that is going to contain sources and resistors and capacitors only. In other words, nothing other than resistors and capacitors in addition to the sources that we're using. So let's pick a circuit, okay? And let's say we have this circuit right over here, and first question is, does it meet our requirements of being an RC circuit? Sure does. There's a source, and other than the source, everything else is either a resistor or a capacitor. Now, Michelle, when we talked about capacitors, we said capacitors have a certain property in DC. Do you remember what that was?
Let me guess, the big red letters. They look like open circuits.
That's right. They do indeed look like open circuits because they're plates, and in DC they're essentially like insulators. So what we can then do is, if we want to figure out the DC behavior of the circuit, anytime we see a capacitor, we treat it as an open circuit. So we take the same circuit that we over here have on top, and we redraw it in the bottom in the DC form, and in the DC form, every time we saw a capacitor, we removed it and replaced it by an open.
Oh, I get it, because if you wait long enough, essentially, if you wait for all of time, nothing's been changing, everything's at DC, this circuit will settle to these voltages V1 and V2. You can solve for them like any circuit without a capacitor, like any linear circuit we've been doing for this whole class. So you can essentially solve for the voltages that the capacitors have initially.
That's right, and you said something pretty important. You said if you wait till it's done responding. And what are you talking about? You're talking about the point after the transient is done.
That's right.
So that's basically what we're talking about. Now, let's see how we're going to solve this circuit. You look at the circuit and you recognize right away that you could solve this using a KCL, for example. If I want to find the voltage V over here, I could solve it by KCL. And so we can just set up the equations to solve it. We can find the relationships on the various branches to solve. And it turns out, if you do the math by simple KCLs, you can find the voltage. And the voltage V turns out to be 16 volts. V, of course, is the voltage across the capacitor C1. So we get V1 is equal to 16 volts. We can similarly solve for V2, and V2 turns out to be 10 volts. The point being that these RC circuits are easy to deal with in DC. It's everything you've already learned. Just take every capacitor you see and replace it with an open. Now we get to the more tricky part, which is to start figuring out the transient response.
All right. So what we're going to do is we're going to look at how a charged capacitor, when combined with a single resistor, behaves. We're going to first do the response, what's called the natural response, and I'll explain that in a minute. And then after we do that, we're going to come back and look at it when there's actually a force response added to it.
So if I remember right, we agreed that natural response was the behavior of a circuit when we do not have an external stimulus. So I assume what you're going to show me here is a situation where the response I'm studying is when there's no externally applied voltage.
That's exactly right. So let me walk through these three diagrams and outline exactly that. What we're going to do in the short version is we're going to take a capacitor and connect it in series with a resistor. And we're initially going to charge that capacitor using an independent source. Okay, and I'm going to solve for what condition that leads to. And once we've done that, we are going to switch this switch from position 1 to 2, and it's going to just isolate out that source and leave us with a situation where it's just a capacitor and resistor by themselves, no other source. And this is where it's going to naturally respond, where you're going to get the natural response.
Okay, so let me see. I think there's two things you said. You're saying we initially solve it in DC, and that's why you've taken out that capacitor and made it an open. Mm-hmm. And so I'm sort of assuming that that source has been there long enough, so this source VS has been there long enough that it's charged up the capacitor and now it looks like a DC situation.
Exactly.
And then what you're doing is at time t0, you are basically closing the switch. You've now removed the voltage from the system, and so now what you're going to give me is the natural response.
That's exactly right.
Makes sense.
So let's go through that slowly. At t equals 0 minus, and what does that mean? T equals 0 minus is defined, that's what the little minus signs mean. It's just a little notation. It's just the instant before the switch is moved from 1 to 2. So initially we're going to start there. At t equals 0, we're going to flip the switch. And t equals 0 plus is another little shorthand to mean for the immediately after, and it's, in our case, it's just these two things are going to be synonymous, okay? Now think about this for a second. Because the voltage across the capacitor can't change instantaneously. We talked about that when we were discussing capacitors. It just can't. It must be true that the voltage on the capacitor at time equals 0, just after the switch is flipped, has to be equal to the voltage just before the switch was flipped.
Okay, I understand. Because the capacitor cannot have a voltage across a change instantly, despite the fact that I'm closing the switch, as far as the capacitor is concerned, the voltage stays the same.
The voltage at that instant, across that instant, stays the same. So what is the voltage before we flip the switch? That's easy to figure out, as you said. Before we flip the switch at T0 minus, this thing doesn't do anything, and we just have a source, a DC source, a resistor that's associated with that source, another resistor, and the capacitor. Now, we've left that there for all of time, from T minus infinity to 0, it's been sitting there, which means that it's essentially a DC. And so we can solve for what this voltage is. Now, we all know this is a very simple example. If this is an open, there's no current going down this branch, so what's this voltage?
It's going to be the source voltage, Vs.
Vs. So we know that Vs, the source voltage, is the voltage on the capacitor right when the switch flips. Okay? And that means that after the switch flips, that instant, just that instant, the initial condition of this capacitor is to have a voltage of Vs. That's the trick. That's the whole trick.
I see. So the trick part is this first equation here.
That's the whole trick.
V0 is equal to V0 minus.
Right.
That's the trick.
That's right. And so we start with a capacitor initially charged to Vs. Now, once that's done, we know the initial condition for our math. We know that the initial condition is that the V at t equals 0 for this capacitor is Vs. And we also know by KVL that R times I, that's the current I running through it, equals, plus V, where V is the voltage drop on the capacitor, equals 0.
Now, I should point out that you see these are lowercase. Given the nomenclature, that's because here we're allowing for time variance.
That's right. And so now we can add one other thing, which we know that the relationship between the current and the voltage on the capacitor, we know that I, which is the same I that runs the resistor, equals C dV dt. So we can substitute that back in, and what you'll get is RC dV dt plus V equals 0. This is a very common equation. Okay, it's got the function and the derivative of the function equal to 0. It's very common in applied math. And to make it so more formal, you always try to clean up the coefficient in front of the biggest derivative. And so you get dv dt plus AV equals 0, where A is just 1 over RC. Okay, so now the question is, for the next couple slides, is how the heck do we solve this? What is the solution to this equation?
Okay, so this rearrangement you did was just to get it in a standard form. I mean, you haven't really changed anything.
No, that's right. I mean, it's just a standard form that people like to see in applied math, basically.
Okay. All right. So now what we can do is we can go ahead and start solving this problem. So we have the standard form equation, and I need to know how to solve it. Now, I'm going to do something now where I'm taking advantage of things I already know. So this will be a little unsatisfying, but I'll justify it at the end. Okay? Here's what I'm going to do. I'm going to take that standard form equation I had on the previous slide. In other words, dv dt plus A is equal to 0. And I'm going to multiply every term in that equation by exponent of AT. You agree that the equation hasn't changed because everything got multiplied by the same value. But you're probably asking me, why are you doing this?
Where the heck did you get that?
Where did this come from? Well, it turns out it's pretty simple. I know how to get to an easily solvable answer this way, and I'm taking advantage of the fact that the derivative of an exponent is related to the exponent itself. So if I multiply everything by an exponent, it makes my solution easier to come to.
But the guy that first figured out the solution probably didn't do it this way.
That's right. The guy who first figured out this form actually had to go through it to sort of figure out how to solve it. Okay. We know how to solve it, so that's why we're doing it this way.
All right.
Fortunately, we're not going to ask you as students to sort of derive this yourself. No. You'll start from this point.
Okay.
Okay. So now, if you look at these first, at the left-hand side of the equation, you'll notice that the sum of the first two terms is in fact just the expansion of the differential of V e to the AT with respect to time. Right?
In other words, what you're saying is that the derivative of V e to the AT is
the left-hand side.
Right, because it's in parts. So
correct.
Right, there you go.
That's right. The derivative of this with respect to time is what's shown in this equation on the left-hand side. So therefore, what we can do is we can take this equation, dv dt e to the AT plus AV e to the AT is equal to 0, and we can rewrite it as the derivative with respect to time of V e to the AT and say that's equal to 0. So now we've got a very simple first order equation. We can integrate both sides to start solving. And so what we're going to do is we're going to integrate both sides with respect to time. The left-hand side is going to be an integral from 0 to t of that differential. The right-hand side is just going to be an integral of 0. So we know how to proceed, and we can go ahead and do that.
So easy enough. So if we take the integral of that just by observation, that's going to give you v e to the at, right? Because there was a differential in front of a d dt from 0 to t. So substituting that in, that gives you that the voltage on that capacitor times e to the at minus the voltage at 0, right? Because there's a 0 there that goes to 1 equals 0. Now we just have to rearrange and solve for v of t. Pretty straightforward, and here's what you get. And this is really the result. What this tells you, after what some of you might have found a little bit convoluted, but it's worth the trouble of going back these two slides and making sure you followed us, is that the voltage for all of time after the switches, right? The capacitor was charged, we switched it, and now we let the resistor and capacitor do whatever they wanted to do. What they do is, it starts at this voltage at 0, whatever that value may be, and then it decays, it drops, according to e to the minus t over RC. This is the most important part. This is the natural response of a single resistor and a single capacitor together in a loop. What happens is it starts at some initial value, which we solved for in the last 2 slides ago, which is Vs, and then it just drops as e to the minus t over tau.
Okay, let me see if I understand that. So that initial value that you add over here was calculated from the DC response.
That's right.
And then once we switch it into the natural response configuration, it just decays.
That's right. And this thing is called the RC time constant. And the RC time constant tells us, if you'll recall a few slides ago, we did a few examples of transient responses. The RC time constant tells us how fast the decay is. And I'll show you an example, or Vivek will in the next slide. But depending on how big or small this is, the exponential will decay, at a certain rate. And not surprisingly, the unit of this is in seconds, both because this is a measure of the time constant of the circuit, as I said, but also mathematically, because these two things have to have the same unit, so that the exponential doesn't have a unit in its term. So, Vivek, why don't you walk us through, sort of sketch out, and I'll jump in, how, given a certain voltage, this voltage we just discussed, e to the minus t over tau, the current and the power and the energy sort of change across a capacitor.
Sure. So we've already got the voltage response, right? Because we already set that up. We got the current and voltage behaviors from the natural response equation on the previous slide. So what we had is, in the DC configuration, the capacitor was charged to Vs, and then, as Michel just showed you, it decays away, and it decays away with an exponential minus t over tau, where tau was calculated from RC. Right? So we have the voltage behavior. We can then find the current behavior by just taking advantage of the fact that we know for a capacitor, the current is just C dV dt. Okay? But we know dV dt, that was the natural response equation we have over here. So we just end up taking the derivative of it, and the only big change is it's still an exponential, but because we had a minus t, a minus sign shows up. And so what we have then is we have a current that starts negative, and then it rises up. Now think about what that means. If we look at the capacitor, so I'm going to back up 2 slides so that we can see this. Okay, here's what we have. We had this capacitor. It was at time t is equal to 0 plus, it was charged up. And we are now discharging the capacitor.
Oh, so this I is going to be flipped in the opposite direction.
Exactly. So remember, our I is defined going into the capacitor, and now we're discharging the capacitor, which is why when we come over here, we have a negative current, and then over time it sort of asymptotes to 0.
So initially it starts at a voltage, and that voltage is slowly decaying as it discharges, and that corresponds to a large efflux or exiting current, I guess, from the positive terminal of the capacitor, but that drops off over time because eventually the thing just empties out.
Right, you're discharging the capacitor, it goes away over time.
Cool.
Now the next step is to calculate power. That's pretty easy. I'm going to multiply voltage and current together, and so you will get a curve that's the multiple of these two, and that's shown over here. And then you can integrate this with respect to time to get the energy, and that's the energy curve shown over here.
And not surprisingly, the exponent of the power has a 2 in this, right? Just like these two things are multiplied, you get this 2 up here in a way that's analogous to what we discussed concerning
Correct.
AC power. Great. Okay. So now, having done that, what I want to do is jump a little faster through the general response. Now, what do I mean by that? I mean that it's a situation that's very similar, except after you flip the switch, in other words, when you're solving for the response of the capacitor, we also introduced another source. So let me walk you through that. The initial part is the same. So this initially does nothing, this VS2. You have a VS1 that's being used to charge this capacitor. This is the same as we did in the first problem.
I see. So we're going to use the same DC analysis, and we get to ignore this
right.
source because it's not connected in effectively right now.
Exactly. And so your VS1 here is going to work out just as we did before. Basically, the voltage on the capacitor is VS1 when time starts, when for t greater than 0.
Okay.
But this time when we flip the switch, so that initial condition is the same, but this time when we flip the switch, we're not flipping the switch where this is just, it's just, you remember, just an empty branch, it was just a short. Now there's going to be another source here. And all we're trying to mimic here is a condition where we first charge it up, but then we flip the switch and the capacitor can't just discharge to 0. It can't completely drain out. There's something else that's forcing it. That at t equals infinity, even after the capacitor is done changing however it wants to change, this thing will force it to do something. And that's what we want to see it happens. It'll turn out that it's pretty analogous the way we solve it. So first things to repeat, the initial voltage on the capacitor, because it can't change instantaneously, you solve it for the DC case, and that's going to be the same voltage that you solve for the DC case. In other words, VS1 is going to be the voltage right when the time begins for t equals 0 plus for this problem. Now, once we do that for t greater than 0, we just do KVL around this loop, and we get minus VS2 plus IR plus V equals 0.
Okay, so it looks like so far we're pretty similar, except now we have that extra minus VS2 term in there.
Exactly.
So I'm going to guess that when we write the differential is just going to have an extra term corresponding to that.
Exactly right here. So when we stick I into here and rearrange again into the standard form, we still have this A, which is the 1 over RC term that comes from the natural response of this thing. But now there's this B thing, which is representative or related to the forcing.
I see. And in the previous case, it was equal to 0 on the right-hand side, but now it's equal to B, where B is VS2 over RC.
That's right. And so now when we do the next slide, when we do the integration, you remember here, when I started last time, there was a 0 here, right, where you left off. There
right.
was ddt VE to the AT equals 0. Here it equals BE to the AT. But that doesn't cause any problems because when we integrate the left, instead of integrating the right and it was just 0, we just have to actually integrate this. But,
Yeah, that's not so hard. That's an exponential. Those are relatively easy to deal with.
Exactly. So what happens when we integrate both sides, we're going to get this is the same as last time. This part's the same as last time. It's VE to the AT, 0 to T. On the right side, we're going to get this A here, so we're going to get B over A, E to the AT from 0 to T. So evaluating all of this stuff at these two limits from 0 to T, we get this part, which again is very similar to before. So the voltage across the capacitor, E to the AT minus V0 equals this gobbledygook over here. And solving and rearranging, we get this. Now, this is the part that's worth going into in more detail.
Okay, so look at this equation carefully now. What we have over here, we've got V of t is equal to the sum of two terms. The first term should look familiar to you. Michelle, do you recognize the first term?
So that looks like the sort of natural response. It's the decaying thing that the capacitor did on its own.
That's exactly right. So it has the initial value, the DC calculated value, and that is e to the minus AT. So that is the natural response. Now what's happened is, in this new circuit, because we had that source in there, there's going to be an additional term that corresponds to the impact caused by that source. And that's the second term over here. This is coming from the solution from this original equation where the right-hand side was no longer 0, rather there was b e to the AT. Okay? So that's where this term comes from. Now think about what this means. Let's take the case where we wait long enough. Okay? So we're going to wait till time is equal to infinity. Okay? Let's back up. Before we get to the equation, let's back up and look at the circuit. So just forget the equations. Look at this circuit. I'm going to wait till time is equal to infinity in this configuration. What's the voltage going to be on this capacitor, Michelle?
Well, if you wait forever, that's a DC source. And so I guess that capacitor just looks like an open.
Right.
Right, just like before. So if that capacitor looks like an open, there's no current through the resistor, so the voltage across that capacitor has to be VS2. Oh, so what you're saying is that when we go back to that expression in a minute, the answer at t equals infinity better be VS2.
That's right. So let's do it. Let's go ahead and go to that, and sure enough, at t is equal to infinity, what the answer simplifies down to is VS2.
Oh, that's right, because this exponential goes to 0, so
Correct.
This whole term goes 0, and this part goes to 0, and you're just left with b over a.
That's right. So what happens is the natural response goes to 0, Okay? If we look at the component that corresponds to the force response, the part that's exponential at time is equal to infinity goes to 0, and so we're just left with B over A, and B over A, based on the equations previously, is just equal to VS2.
So that works then.
Yeah, this does work, and this is the basic idea behind general response, so you can see how these come together.
Okay, so I think on the next slide, I think what we want to do is just rearrange it a little bit to give you an analogous or a complementary, rather, view of this. So you saw that we have this expression. Vivek just went over it, and we saw that at v equals infinity, you get this. But let's tweak it around a little bit. And what I want you to convince yourself is what's in this blue box. If we acknowledge that tau is 1 over a, and that b over a is equivalent to the answer at infinity, in other words, v at infinity, so whatever that value may be, I can rearrange this into this form.
I see. So what you're going to do is you are going to take this b over a, and you're going to replace it by v infinity, right?
That's exactly right.
Okay, makes sense. That's easy enough. So I do that, and this is what I get.
Yeah, then I'm just going to factor stuff out. But why do I do this? What's neat about this is that it shows you that the total response of a capacitor, when in a situation where there might be a source or there might be something forcing it, is the steady state, this v at infinity, what it's eventually going to hit, plus the part that decays out between the initial state and the final state in an exponential fashion. It's just another way of doing the same thing. These two things are the same. It's just different ways of kind of thinking about what the capacitor is doing.
I see what you're saying. And now what's kind of neat about this is this makes it into a form that's perhaps a little more intuitive. I'm saying that ultimately it'll reach my steady state value. So whatever is not multiplied by that exponential is what I'll finally end up at.
Right.
Okay? And then what's going to happen is at the initial state I'll be at v is equal to 0, and then I will decay down to the value at v is equal to infinity, and I'm going to decay exponentially.
Exactly.
Makes sense to me.
Yeah.
So this is the generalized response of a first order RC system. In other words, a circuit that has a resistor and a capacitor and goes through this sort of switching action. This, by the way, you could collapse back down to the natural response, because in the natural response case, the v infinity would be 0.
That's right, exactly right. So when you put 0, all that stuff goes away because these two terms go, the v infinity terms go away.
Okay. It's also more general than that. In this particular example that we looked at right over here, we switched at t is equal to 0. If you are shifted such that you're switching at t is equal to 5 or t is equal to 10, just take the entire equation and shift it around. So you can do that over here. Here's the more general form where instead of switching at time t is equal to 0, we switch at a time t0. Everything just shifts to accommodate that, but the equation itself doesn't change. So at this point, we've done a good general introduction. What we're going to do in the next module is we'll do a couple of examples so you can see how this works. But before we do that, it is certainly worthwhile for you to go back and review the math and make sure you understand each step in the calculations that we did. Because we went through it, we explained why we did it, but it certainly helps to go and look at it again to be sure.
Yeah, I agree. And hopefully the examples coming up will just help you get used to the sequences over and over and over again. All right, see you soon.